momentum, little p. Object mass m, moving at speed v. The technical word is really linear, linear momentum. What was that? How do you get linear momentum? What's the equation for it? If kinetic energy is 1/2 mv squared, what's linear momentum?
Would it be the square root of ke to m?
Oh, yeah, you can solve it from there. But it had its mv.
Oh, I see.
And then we're going to use those.
Oh, so I have to use that. Okay.
Yeah,
so
we're going to use
1/2
these
mv
two equations.
To that, right?
So we're going to use these two equations to derive this relationship. So that's something, we're going to put that as a you do. That's something you can work on. Okay, 'cause pretty much all you do is you put in, by starting with the kinetic energy. So start with 1/2 mv squared, and then substitute in your p, and it'll work out. Let's work on where we really need our help here, I think. This is where we really need to remember stuff. The first derivative, d dx, was also written abbreviated f prime. Remember that? The second derivative, d2 dx squared, was also written as f double prime. Yeah. Okay, so I'm just making sure you remember that. So let's find f prime. Take the first derivative of kx, you would just get?
X was my k the constant?
Yeah, k is just going to be a constant.
So it's going to be x.
Yeah, so again, if you recognize that equation, it's just going to be x. That's the equation for k was a spring constant, and F was a force that was needed to stretch a spring, but we'll be getting at that later.
So that would be...
So F prime would just be x.
Oh, it wouldn't be k, because we're doing it with respect to x.
Ah!
Oh, okay.
Thank you, sir. You're awake, I'm not. Right? Okay. Okay, how about B, F prime? Now, there's two things you're actually doing to that x, right? And you always start on the outside, then you work your way in. So what's the most, if you're going to actually find this on your calculator, what's the last function you would do of those two? Would it be the cosine part or multiplying by a part? The last thing you would do.
Oh, multiply by a, I would think.
If you're going to do it in your calculator, don't you have to multiply by a? Because you have your x. It's a variable, so it can be anything.
I see what you're saying.
You plug in your x, and then you multiply it by a. That's the first thing you do. Then you take cosine.
So it doesn't become part of the cosine.
So the last thing you did was cosine. So the cosine has to be the derivative you take first. And then it's a. Right? So if you take the derivative of the cosine function, what do you get?
Negative sign.
Negative sign. So you exactly right, put it in. And it doesn't matter what's inside that cosine. You have to write it out because you haven't messed with it yet. Okay? And then you take the derivative on the inside, and then you get your a. Good. All right, so usually they like to write constants out front, though, right? Because then it's not confusing what's inside your trigonometric function. Try this one. I see three functions there. Recognize the outermost one, and that's what you take the derivative of first. If you don't quite see it, imagine x is your variable, and you have to plug something in for it. It's 30 degrees. So first you'd multiply it by k. And then you take the cosine of it, right? And then you push the what button? You'd square it. You follow that? If you're going to actually find the... And then you multiply it by 2, I guess. You see all that? So if you're going to do it on the calculator. So what was the last thing I said? The last thing I said was squaring the cosine part.
This is a product rule, right?
Technically it's called the chain rule. Because you just keep going. But you start on the outside function.
Problems with that cosine squared.
So what's the derivative of anything squared?
You're going to
Bring the 2 out front
One less.
and one less. So let's do that. Now that 2 is the original 2. So let's bring that 2 out front. And then you said it's 1 less. Okay, so now we just did the most outer function. Now you don't look at what we wrote, you go back to that function. What's the next part?
Then you gotta multiply times the k. Which
Well,
is
no, you skipped one.
Oh, the cosine?
The cosine function. You haven't done that yet.
That's right.
So
It's
what's the derivative of the cosine?
Negative sign.
Negative sine. And again, you don't even care what's in that integral. Sorry, what's inside that. You just keep copying it. It doesn't matter how complicated this part is. You just keep copying it.
Then we multiply by the k.
Now we're finally on the inside. Then you multiply it by the k. And I guess they'd like to write the k way over here, right? So I think it looks better too. It might be harder to explain to somebody if you're trying to teach them how to do this. But it makes more sense, put all those constants way out front. Okay. How about this one?
Okay, so it'll be 2 times e to the negative kx times negative k.
All right, you remembered something, right? The
Everything.
derivative of the exponent of anything is just, it's the same thing, right? So he has his 2, and then he said what? E to the negative kx, and then times
Negative. K.
negative k. I guess I should have put that with the 2, but all right. So a negative 2k times e to the negative kx. Okay, let's try these now. So we have the first derivative. Now we just gotta find the second derivative.
So that one, the first one would be gone.
Yeah, so on this first question, on A, my second derivative is just going to be
0.
0. Because k is just, think of it as a number, 6. It has to be 0. Next one. Try to write it out. So Richie, what'd you come up with?
I'm still waiting. Can you do chain rule for this one?
You have to,
Okay,
because you're doing more than one thing to that variable.
I see. So, did you get?
What do you get? This we got to start somewhere.
No, go ahead.
Rick, you got to start somewhere.
I got, going from the A side. I said A times the derivative of the negative sine ax, which is negative cosine ax. So
Okay.
negative cosine
Okay.
ax to the right.
Okay, I'm gonna just help you out a little bit. I see exactly what you're saying, and you're exactly right. That negative a, you pull it out front. You don't even. My brain doesn't even want to look at stuff it doesn't have to. So this stuff, I don't want to see it. All I want to see is that sine ax. Your brain is so much easier. And the derivative of and I don't even look at the ax in here. I don't care. The derivative of the sine is
Negative cosine.
Well,
sine is cosine, right? So that's the first, and I don't even. So I wrote the negative a,
I see. Okay.
right? The cosine, whatever was in there, you don't care. And then the derivative times what's in there, which is going to be a. So I guess you could write negative a squared cosine ax. Okay, you probably had the same thing.
Yeah.
I'm just trying to make it, because it's going to look even uglier in the homework.
Hey, if it helps.
Because they're not going to have a's, they're going to have 2 pi over 6 or what, right? It's going to look uglier. So just try to try to not look at what you don't need to look at.
Yes. And then I put
Okay.
plus a negative, so just negative cosine AX.
Okay. So are we done with that one?
Yes.
Yeah. Now let's try C, F double prime.
What was the second part
Oh,
to it?
there was a second part, I believe. But
Yeah, don't you take the derivative of the second times the first?
well, no, I'm sorry. I thought product
Wait,
rule was this times the
you
derivative
hold
of
it.
that plus this times
Are you talking about B or C
I
now?
was talking about B.
B? We're
Yeah.
we're done.
I see.
There's only. It's not like you
I
have.
see.
It's not like you have two functions.
That's what I was asking about the.
A's a constant.
A is a constant. All these letters are constants. X's are.
Yeah.
They're,
Okay.
I guess
gotcha.
I guess the notation
I gotcha.
is trying to tell you that.
Somewhere over the break, I guess my brain thought.
But we're gonna need what you're talking about.
It's not.
Hang on to that thought, but just save it for 10 seconds. Right? That's the next one. But d dx squared, from all this stuff, this tells you what the variable is. Right? So everything else is going to be a constant. So x is the only thing that's a variable. Now we can talk. Now, Ricky, talk about what you were saying.
Now I don't. No, it's okay.
You were saying
Okay.
that I think you were saying there's two functions of x.
Yeah, want to do the product rule really bad, apparently.
Okay. Now, this is how I remembered it. There's an equation for this. But I just remembered as, and this is how I always do it. You might have your own method. The derivative of the first times the second plus the derivative of the second times the first. Does that make sense? That's how I remembered this. So I have to figure out what my first and my second is. So I'm going to call this my first and this part my second. Doesn't matter, right? But everything's included. So let's take the derivative of the first.
Times the second?
Yeah, so let's take the derivative of the first.
Okay.
Sorry.
But now remember, don't help yourself out
Negative.
by doing this first, right? And then you say negative sign, and then you copy down whatever was there. Okay, we're not quite done yet.
Times the second.
Well, no, you haven't finished taking the derivative of, there's an inside function,
Cosine kx times k.
times k.
Go back and make k squared.
Oh, yeah. Yeah, less writing. Okay. So that is the derivative of the first times the second. Times the second, so we could just write what?
Sine squared.
Sine squared. And make that a positive. Right? But if this is your first time and you're trying to remember this stuff, you may not want to do this shorthand notation stuff. You may want to write times the negative sine kx. You remember what the hell you just did. Okay. Plus.
Now I think I'm a little confused. I'm sorry. On that, what do you call it? What did y'all do to get that sign times another sign?
I just times the second part. You take the derivative first and you just times the
Okay.
second part.
Got it.
Derivative of the first times the second.
Got it. Okay. Thank you.
Plus the second. So let's go ahead and write it so we don't screw it up.
Well, how was the derivative of the second plus the first? I mean times the first.
Derivative of the first times the second plus the
Derivative of the second.
derivative of the second times the first. I should write it down. All right. Thank you. Okay, so I take the derivative of the second.
So that would be cosine.
Yeah, because those negative signs are going to cancel out. Cosine kx,
What? You want the k in front of
and then
k.
put the k out front. Since we have parentheses, we could kind of put it on the end, I guess. Derivative of the
Yeah.
first times the second. See, but how I said it was derivative of the first times the second
I mean derivative of the second times the first.
plus the derivative of the second time. Oh, I did say that. Okay.
Yeah, but just times the first.
Now, the first. Copy all that stuff. What is that, a 4k
Yeah, so you write k squared.
cosine kx? Oh, yeah, you could.
Well, actually, you write k squared cosine squared.
Yeah, I have a 4. Right? So you could really say f double prime here is 4k squared. What was sine squared plus cosine squared?
1.
It was 1. So the answer is really 4k squared. Okay, that was C. Okay.
Can you simplify it that way since you have a 4K2 and 1?
I have 4k squared and a
I
4k
see.
squared, so I
Yeah,
just
you
pulled it out.
Pull it out. I see.
Okay, so and then you do D. That one's not too bad. So the you-dos is just homework.
Whoa, can you go back up? I'm sorry, I really copied. I was trying to understand it.
Where did we lose you?
I was trying to figure out if that second part, it was negative or not.
Oh, the negative sign's canceled out because derivative of the sine, isn't that right? Oh, we screwed up. Derivative of the cosine is a negative sign, isn't it?
Yeah. And derivative of a sine is cosine.
Oh, but it's derivative. It's derivative.
Yeah, you keep the negative, don't you?
Yeah, so we lost our negative sign, didn't we?
On
Well-
yes, on the second part.
Yeah.
Didn't we lose our negative sign? We forgot our negative sign.
So what do you?
It wouldn't be 1. I thought it was going to be a nice, clean problem, but it's not. Yeah, we can't get it. We can't get a 1. I thought it would be a 1, but it's not. That's okay. Okay, so one more time. Derivative of the cosine is
Never sign.
negative sign. Derivative of the sine is
Cosine.
cosine. Okay. Yeah, that was up here. We did that. I forgot. Okay. Differential equations. Okay. Yee-hee. Now, I'm not going to teach you everything about differential equations. The point is it's intimidating. I know that. But honestly, if you can take a derivative, you can do integrals. If you can take a derivative, you can do differential equations. All you do is remember the rules for taking a derivative, and it's very doable. And we're not going to mess with the entire course of differential equations. We just want to know how to manipulate and handle what you're going to see in this course. Okay. So that's all. We're not worried about any concepts at all right now, just how to plug and chug. So we're going to substitute this function into the below differential equation and then simplify it to get an answer that's going to be something, some constant, and then we'll get our function back again. Okay, and that has some real significance in this class. So let's try it. So we're going to substitute in our y here. Can I erase that? I can't. I'm just write the whole thing out. Let's see. This mess is going to be negative h bar squared over 2m. The second derivative. And substitute in my function. A e to the I kx and b e to the negative I kx. Okay. So we have to take and use that in math notation, you know, and it really helps. It's a stickler. You really got to be anal with math notation, right? So it would look like that. This would be the first thing you do. You don't care about what's out in front of that derivative. In fact, if you had more constants, pull them through so it'd be cleaner and easier to take derivatives. But I wrote just d dx because inside the brackets I'll have the first derivative. Okay. So you take the first derivative of a to the e to the I, a times e to the I kx, you get, what would you get?
Derivative of what?
The
E to the
derivative.
I,
Yeah, this
e to the I kx?
this mess right
Oh, I
here.
see.
We'll take the derivative of him first, and we'll write it
That
right
would
here.
just be all of that, right?
You'd have all of it again.
And then do it with respect to x?
In fact, you don't even have to worry about, again, make your life easier. Pull out the a. You don't even care about it. All you're really interested in is e to the I kx. So what's the derivative of e to the I kx? E to the I kx again.
And then with respect to x, right?
Yeah, so we're not quite done, though.
Then times I k.
then times ik. Same for b, just negative. Exactly. Just get it right. b e to the ikx. Ah, it's supposed to be negative, right? Negative ik. So the derivative of the exponential is just the exponential again. Now we got to take our second derivative. Okay. So what part should you not even be looking at? And this, taking this first derivative here. What part do you just pull right out? AIK. Don't even, try not to even look at it, right? And then your life is so much easier. What's the derivative of IKX? E to the IKX, sorry. E to the IKX times IK again. Right, because it's everything in front of that x. Has to be constants. Yeah, it is. Okay. And now we can, would we pull out so we don't have to look at it? Yeah, minus IKB. Or however you want to write it, BIK or whatever. It's all. Derivative would be e to the negative IKX times negative IK. Yeah, we got to clean it up because see what they wanted? They wanted us to get back into this format. So somehow we got to clean this up so we get our function back again. And remember our function is this. So we got to clean it up. You're right, we're going to have to be squaring stuff and trying to get it fixed up. Okay, so see if we can fix this up. So we have our negative h bar squared over 2m. Okay, can we pull anything else out? Or should we just let's just simplify what's on the inside before we try to pull more stuff out. How could you simplify this first term? This is the first term. Everything's multiplied together, so I call it the first term. What would that be?
Do you want to put ik squared together, or do you want to put I squared k squared?
We want to get this. So we put the, I would put all this stuff together. You got to get rid of it. What would that be if you put it all together?
AI squared k squared.
Okay, now what was I squared?
-1.
I squared was a -1. So that would be a negative a k squared.
We're using I as an imaginary number.
Yeah.
So wouldn't that be a positive one then? -1 times -1.
Square root of a -1 times the square root of a -1 is -1. It's like square root of 2 times square root of 2 is 2.
Oh, okay.
Okay. Then the next part. What would the next part be?
So now it'll be a positive one?
Now it'd be a negative one.
No, now it'll be a
The
positive.
next term.
Minus b.
Oh, wait.
Remember
I'm
these?
a little confused because there's 3 negatives.
Those 2 negatives are gone. Don't even disregard them.
So that's what I was saying. Are you going to
But then
mess
the
with
I
that
makes
now?
it negative.
These negatives are gone. So what's I times I again?
Just -1.
-1. So what would be the rest of it?
K squared B.
K squared B.
Good.
E. Negative IKX.
Yeah. Now can you see it? Now you just pull out what, and we'll have our function back again.
K squared.
Close. Our function was this.
So you have to pull out negative.
Pull out negative k squared. Pull out negative k squared. Pull out a negative k squared, so its negative signs are gone on the outside. So this constant that they were all worried about, that constant is right here. That's that constant that they were worried about. You got your function back again. Okay. So there's real significance to this expression in the molecular nature of very, very small particles. And there's real significance to this operation, where you get a constant and then your function back again. Okay. And we'll get into that in the classroom. Using integrals, integral tables, and trigonometric relations in solving complicated integrals. Okay. So again, this is probably like Calculus 3 or something, but again, with a little, these are really the only two formats that we need to worry about and we need practice with. Okay, so if we wanted to find the integral of sine squared, well, we just need to do this, and then we can solve it. Okay, otherwise we're not going to be able to work it out. Okay. So let's see if we can remember how to. So substituting is not so bad. Let's see if we can remember how to take integrals. And remember, integral is just not a derivative, but
It's like a
backwards. Antiderivative, but going backwards. So we can do it. So this is going to equal the integral. I'm just copying everything, and all I'm doing is substituting in for sine squared theta. And sine squared theta is this whole big mess. If I'm going to use this substitution, though, what does my a have to equal? What would my a have to equal? It's defined right here. What does a equal?
1.
A has to be 1. Otherwise, you're not going to be using this expression right? Because in this expression, my a has to be 1. So that means just looking at this, a has to be 1. So I'm going to substitute in that expression using a being 1. So I'll have 1/2 1 minus the cosine of 2 theta. Because right here, sine square theta, sine square a theta. These two things have to be the same. They have to be the same. So the only way they're the same is if a is 1. A can't be 2, because then this would have to be 2 theta. If my integral was sine squared 2 theta, well then my a would be 2. Okay. Now with integrals like this, do you remember what you did? I remember what I do. I just kind of make this multiple integrals because it's so much easier. I mean, if you're good at integrals, you can probably do all this in one step. Me, I don't memorize jack, so I'm going to make this, bring that d theta through and make this 2 integrals. When you have minus or plus anything, an integral is just what? What does an integral represent? What under the curve? Area. So you can add areas, you can subtract areas, it's no big deal. So let's break that into two areas then. The integral from 0 to pi of 1/2 d theta minus, and let's pull that minus sign out of the integral, you don't have to worry about it. In fact, we could make our life easier by pulling that 1/2 out of the integral. Can you do that?
Yeah.
Yeah. The only thing you can't pull out of that integral is what? Anything to do with theta. You can pull anything out of that integral as long as it's not theta. So that'll be a lot easier antiderivative to take. So let's pull that minus sign out too. So we'll have the integral from 0 to pi of cosine 2 theta d theta. Okay. Okay. Now let your notation help you, right? This is what I mean by notation. So I don't care about that half. What I care about is what I write in parentheses. This is the notation that's most conventional, right? I have my limits for my integral. Inside the parentheses is my antiderivative. Okay, so this is what I always ask myself. The derivative of what will give me this? Now again, remember my variable's theta. The derivative of what gives me that? Now what is this? Is it 0? What is that? We never write it.
Constant.
It's a 1. What is that?
Zero.
That's not a 0. If it was 0, this whole thing would be 0. That's a 1. We never write it. We probably should, but it's too confusing to write 1. Yeah, there has to be, right? And we're just too lazy to write it. Maybe it looks ugly, I don't know, but we never write it. So the derivative of what would give you 1? Yeah, remember our variable's not x though.
Theta.
Theta. So you put theta in here. Okay. Now we do the other part. Minus, put your parentheses, because that's my antiderivative thing. Put your limits. Okay. So you don't care about what's outside these parentheses. You're asking yourself the derivative of what gives me cosine 2 theta.
Sine.
Derivative of the sine.
2 sine theta.
Let's just write it. This is what really helps. I write it. That's supposed to be a 2, not a z. Right? 2 sine 2 theta. And then you try it. And life is so, because otherwise you just sit there, think, just try it. So, because taking derivative is so pretty fast. What's the derivative of this? It'll be negative cosine times
Oh, times 2.
2. So you end up with a 4 here,
That's for sure.
right? Okay, so we have 2 things to fix. Pablo noticed one of them. Let's make this a half out front.
Then you have to change negative to a positive.
Okay. Then do what?
Negative to a positive.
I don't know what you mean. Negative. We don't have a negative.
The minus sign to a positive.
We can't.
No.
This is the constant. We don't. Remember, we don't look at that.
We can just add a negative.
We're just messing with inside the parentheses. So whatever we take the derivative of, we want to get this. So we'll do it inside the parentheses. Put it inside the parentheses.
But that will still carry to the positive later, right? Is that what we're trying to do?
Hang on. Put it. Before we answer that question, let's make sure this works.
Okay.
Take the derivative of this. Do you get that?
Yeah.
Right?
Sign would still be
No, because
No.
the derivative sign.
Derivative of the sine.
I know, but we're not using that.
Derivative of the sine. This. No, you're right here. You're right here.
I'm sorry, I'm looking at the one.
You have to look what's inside the parentheses. The derivative of what's inside the parentheses. Do you get that? Yes, you do. Because the derivative of the sine is negative cosine. Right? So negative cosine 2 theta, so you would write that. Then you got to take the derivative of what's inside, take it times a 2. So you really have a negative 2 times cosine 2 theta. I can get rid of that negative 2 and turn it into a positive 1, which is what I need, by the negative 1/2. So you only focus on what's on the inside. So you always ask yourself, the derivative of what will give me this? And this is your answer. Okay, now your question was, can I pull this stuff out? Yeah. Yeah, you can. Okay. But you don't do it now. I'm sorry, you don't do it before your test. You got to make sure it works first. Then you can pull it out.
So now we'll change that to positive 1/2 sine.
Yeah. Yeah, it kind of makes it easier when we evaluate. So we could. So we'd have 1/2 theta evaluated from 0 to pi, and plus 1/2 sine 2 theta evaluated from 0 to pi. Okay. So remember how to do this. So this first part, evaluate this. First you put in what? Remember how to do this? Put in pi, and then you subtract out what you get for you putting in 0. So you would just end up with what? Pi over half pi, pi over 2 minus 0, which would just be pi over 2. I can write pi over 2 minus 0, so you know, right? But it's just pi over 2. Okay. Plus 1/2 something minus something. Sine of 2 pi 0. Very good. He remembers the unit circle. So do it. Well, evaluate sine 2 theta at pi. Put it here. Sine 2 theta at 0 and put it here. Then worry about the half. So you'd have what minus what? 0 minus 0. So it's all this work, you just ended up with pi over 2. Okay. 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 What do we have after this? Okay, we're going to keep going. Well, these would be good for you-dos. All right, just more homework. Let's jump down to triple integrals. Again, I'm fully confident. If you can take a derivative, you can do an integral. Well, if you can do one integral, you can do triple integrals, quadruple. It doesn't matter, because integrals, you just multiply the one integral times another. That's all they are. So it's not that bad. Evaluate the below integral using the function 18x y cubed z plus 3. Okay? And how many variables are in this expression? How many variables are there? How many variables are there? We always like to think of x as the variable, so we recognize that's a variable. There's 3 total. You're doing diffie-q. It's not that bad. You're doing diffie-q now. You just have more than one variable. All right? So let's go ahead and let the notation really, really helps you. Here they're giving you the limits of the integrals. There's our limits. So let's go ahead and just, they're saying find this, where d tau is dx, dy, dz. They're just getting lazy and like to write all that. But let's just try this. 1, 2, 3 integrals, my f. What's my f? It's right here. So I'm substituting everything verbatim into that. So I drew my 3 integrals, and now I write in my f, 18. Well, hey, why don't I help myself out a little bit first? Can 18 be pulled out of this integral?
Yes.
I can pull it out of, I'm not sure which integral is which right now, but I have an x, a y, and a z integral. 18's not an x, y, or z. Just pull it all the way out. Yeah, I don't have to worry about it then. So I have x y cubed z plus 3, okay, d tau, dx dy dz. Okay, so what they're trying to say is your most integral here is dx. So I guess we can put our limits for x here. X goes from 2 to 3. All right, our y goes from 2 to 3. Oh, they all go from 2 to 3. Yeah. Okay. But I don't know, my brain works a lot better if I can take an integral of x dx. Let's just put it all into 3 integrals. Because remember, an integral is just what under the curve? Area. Can you multiply areas? Yeah. So let's just do that. Let's multiply our areas. So we have our 18. So we said this was our z integral. It really doesn't matter, but it goes from 2 to 3. I guess if the limits were all different, it would matter. So the limits, let's write our z integral. And then we'll multiply it by our y integral. Then we'll multiply it by our x integral. So our z integral, where's our z part?
Is it gonna be the last one?
Where's our z part? It's just z plus 3, right? So this is really our z part. So we're going to, as long as everything is here somewhere, we're going to be okay. But let's check when after we got all this. All right? So there's our z part. And technically you should write z equals 2 to z equals 3. Right?
I'm sorry. So you can evaluate.
I can't add, I can't subtract, I have to multiply. So now let's do and does it matter whether it's 2 times 3 or 3 times 2? No. So we don't have to write the z integral first. Just make sure that the limits correspond to the right one. So here's my z integral. Let's do just to be consistent, we call that y. So I'm just following it. Now what's my y? dy. What's my y function? My y part? Y cubed. And my x dx. What's my x part? Just x. If we had more stuff in there, it just needs to be somewhere. Like that 18. You can stick it wherever you want. Because 18 times an area, the order doesn't matter with multiplying. But life is just easier if you pull out all constants, because we have to take antiderivatives. So that's why I like pulling all the constants out. So let's check. If we multiply all this stuff, what's outside of our integrals, what's inside our integrals, we better get our function, because it's got to be in there. And we did, right? It's going to be, it's all there. 18xy in a cubed and a z plus 3, it's all there. Okay. Now triple integral doesn't look so bad. Not at all. Because we can take the derivatives of this stuff. It's just 3 times the work as what we had before. Okay. So remember, and use the notation. It's going to save your back. So the derivative of what gives you z plus 3? And remember, z is your variable now.
Z squared over 2 plus 3.
I hear z squared over 2 plus 3z. Try it. Derivative of z squared over 2 would just be my z. Check. The derivative of 3z would be my 3. Good deal. And do the same for the next one. And it's not plus or minus, it's all multiplying. Good. Y to the 4th over 4.
X squared over 2.
And x squared over 2. So then you would just end up substituting in 18, and then you'd have your brackets. Put in the 3, get a number, minus, put in the 2, get a number, and do that for all 3 of those. And end up multiplying them all together.
So a triple integral isn't, so the triple integral is based only on the number of variables? It's not like the
Yeah.
reverse of a triple derivative?
Yeah, yeah. In fact, if we didn't have an x, if you didn't have an x, right, but they still want you to find this, all you do is just, there you go. So that's triple integrals. It's not bad at all.